Hi, this is Dan from mechanicalpeexamprep.com. Thanks for joining. We're going to get into this problem on power cycles. We'll outline the problem, then if you want to pause and take a moment to try it on your own. Then if you get stuck, you come right back to the video and we'll step through it together. So let's read through and then we'll start with the outline. A company generates 1,000 brake horsepower from a gas turbine, 9 pounds per second of compressed combustion gases, specific heat at constant pressure of 0.239 BTU per pound degrees Fahrenheit. At 1640 degrees Fahrenheit, enter the turbine and exit at 1040 degrees Fahrenheit. For years, the company has thrown away the gases leaving the turbine. Now it is proposed to use the waste heat to generate steam for a low-pressure steam turbine. A 90% efficient counterflow waste heat boiler drops the combustion gases to 650 degrees Fahrenheit in the process of producing 1,000 degrees steam at 900 psia. An 80% efficient turbine expands the steam to 2 psia, which is the condenser condition. A 60% efficient boiler feed pump forces the condensate back into the waste heat boiler. And they want to know, what is the gross increase in power output in horsepower, and what's the steam flow rate in pounds per second? Okay, so there's quite a bit going on in this problem. It's not a particularly hard problem. It's somewhat of a long problem, and there's a few things that are not obvious or some assumptions that weren't quite clear to me the first time I worked through it, but I was able to make sense of them pretty quickly, and I think you will too. So let's start with a little outline of the solution, and then we'll go through the actual steps of solving it bit by bit. The first thing we'll do is draw and label the diagram, which this drawing came with the problem, and I've added some of the other given information to it here. But I'll just jot that down. That's the first step in many problem. Next, we're going to write for the turbine. What we're looking for is the gross increase in power in horsepower. So the whole point of this thing is they had this original turbine which was giving off some hot exhaust gases. They're taking advantage of that to do some heating of steam, and in that steam they're going to put through a steam turbine. So whatever work that turbine does, that power output is additional energy that they get to harness. So that's really what the question is to find W dot out, the work done, the power generated by the steam turbine. And we're going to write M dot delta H, the mass flow rate for the steam turbine cycle, times the change in enthalpy across the turbine, the steam turbine. And I think it's worth noting that this delta H has to be the actual delta H. It's not 100% efficient. It's an 80% efficient turbine. So we'll talk about how to put that into practice, but it's worth mentioning just in the outline that has to be the our delta H has to take into account the efficiency of the turbine. We won't actually know, so we have to work out that delta H, but we won't actually know the mass flow rate. So we're going to have to use this heat exchanger, or they're calling it a boiler, but it's basically a heat exchanger. It's taking the hot gases off the exhaust of the turbine and using that to heat steam. For that, we'll write a heat balance. So we'll say that the heat that goes out of the primary system is equal to MCP delta T, since we know the mass flow rate and the specific heat capacity. And we also know the delta T, so we can calculate what that is. And we also know that it has some efficiency, so it doesn't transfer 100% of the heat, it only transfers 90% of the heat, so we'll have to take that into account as well. And we'll set that equal to the heat transferred into the steam, which we could write MCP delta T for that as well, but because it's steam and we're going to be working with enthalpies as we go around the cycle, we'll write it as M dot delta H. And this delta H has to be the difference in enthalpy between state 1 and state 2, because that's either side of the heat exchanger. And then we'll know H2 by this point, because we're going to use the temperature and the pressure and the steam table to figure out exactly what the enthalpy is at state 2. But to find the enthalpy at state 1, we don't have enough information, so we actually have to work our way all the way around the cycle to get H1. We'll say find H1 by working around the cycle and using the steam table. After that, we'll be able to find M dot from that heat balance in number 3, and then we'll be able to use that M dot to come up to the equation in number 2 and find the power out. Okay, so this is a good spot to pause if you want to try it on your own. If you're not sure what to do at all, then keep watching and we're going to do it right now. So we got the labeled diagram. We're going to start by writing this equation in number 2. So, and with a little tweak when I actually write it, we're going to say W dot out for the steam turbine cycle. I'll refer to that as the secondary cycle because it's harnessing heat from the first cycle, is M dot delta H. But I'm also going to write the efficiency in there because we know the efficiency for the steam turbine is only 80%. And I want to be even more specific. What delta H are we talking about? This is the efficiency of the turbine, M dot. Well, it's H2 minus H3. It's the delta H across the turbine. Now I could have written M dot H2 minus H3 prime. It's another way of showing that it's not a 100% efficient cycle. But if you use the ideal, assuming it's an isentropic expansion, you can use H2 minus H3 and then just include the efficiency here. So that's a perfectly viable way to account for the efficiency. Okay, so we don't know M dot yet. We do know the efficiency. We don't know H2 or H3, so we got to go after both of those. Let's start by going after H2. Well, at H2 we know the temperature and the pressure, so that is a fully defined state. What we can do is we can go to the appendix and go to page A67, specifically appendix 23.c, and we will find the properties of superheated steam. And using the table, we can look up, based on this temperature and pressure, the enthalpy, and I'm also going to jot down the entropy. You'll see why in a bit. Okay, so these are the values that I found in the table for the enthalpy and entropy state 2. Now for state 3, it's tempting to assume that the turbine exit condition is saturated steam because by the time it goes from 2 to 3, it's expanded. It's not necessarily still a vapor. It might have, some of it might have condensed and it might be a saturated mixture. And if that's the case, we don't know exactly what the quality of that mixture is. That is to say, how much of it is a vapor and how much of it is a liquid. So we have to assume that some condensing has taken place, and the only way to find out the enthalpy at state 3 is to assume, at least at first, that the process is 100% efficient. If it's an ideal expansion, then it will be isentropic, which means the entropy will be the same. So I jotted down this entropy here. We can say that at state 3, that the entropy is the same. And we know the pressure at state 3 is 2 psia, so now we have 2 pieces of information. Anytime we have 2 pieces of information, the state is fully defined, and we can find out what the enthalpy is. Actually doing that is a little bit of a task. We're going to make the assumption it's a saturated mixture, and we're going to use appendix 23b, properties of saturated steam. So we know the pressure is 2 psia, and we know the entropy is the same as it was at state 2. So if I go to the saturated steam table and I look at the one that's listed by pressure, I can find the different enthalpy values and the different entropy values for the mixture, and it's listed as follows. So there's 3 values for each. The subscript F means it's a quality of 0 or it's 100% liquid. H sub G means that that's the enthalpy for a gas, so it's 100% vapor. Same for the entropies. And then H sub Fg is the difference between the two. So these are the numbers that we can use to interpolate. So our entropy value, 1.6, is between SF and SG, so that confirms that it is a mixture, and since it's closer to SG, we can assume that its quality is closer to 1 than it is to 0. but let's actually calculate it by interpolating to find out exactly what it is. So to find the quality, we can set up the equation. We want the difference between what the entropy actually is, 1.6667, and the bottom end of the range, the lower number, 0.175. And we'll divide that by the difference between the two, which is sort of the distance between the lower and upper end, 1.7445. Sometimes folks will write SG minus SF, but just realize that SFG is that difference, so you can just use that as the denominator when you're finding the quality. And this equals 0.8551. So that's the quality of the mixture. And since we have the enthalpy values right here, we can use the quality to find out what the enthalpy is at state 3. So H3, now I just want to make this really clear, so we're assuming that the expansion is isentropic, that it's an ideal expansion. We know it's not, and we're going to account for that with the efficiency later, but we're finding H3, assuming it's isentropic, is 94.02, that's the lower end, plus the quality times the distance between the two, 1021.8, and that equals 967.7 BTU per pound mass. It's interesting, if you had assumed that there was no condensing happening and that it was a saturated vapor, then you would use H sub G, which is 1115, and you'd be overstating the enthalpy at state 3, so that would lead to a bad outcome. By the way, there's another way you can come at this. There's another appendix, Appendix 23E, the enthalpy entropy diagram for steam, also known as the Muller diagram. So if you want to do it faster, like if it's a real test situation, this graph basically has the enthalpy on one axis and entropy on the other. So you can use T2 and P2, sort of the way we did before, just looking at the chart to find the point on the chart, and that'll give you H2. You could pick it right off there. And then you can draw a vertical line straight down, which, since the x-axis or the horizontal axis is entropy, that's assuming it's an isentropic expansion. So then you just find the point where the pressure is 2 psia, spot that point, and now you're using basically you're using S2 without actually having to find what it is. That's what that vertical line is doing. So you're kind of using the fact that S2 equals S3 without bothering to grab the number, and the fact that you know P3, and those two pieces of information taken together allows you to specify the enthalpy of state 3. So the advantage to this, it's quicker, you don't have to interpolate. The disadvantage, it's a little less accurate potentially. If you're trying to, if the numbers that you're working with are between lines, you may have some error. So it really depends on how much time you have and whether the numbers you have happen to be on the line. If you have time, I think it's great to do it both ways, as using the diagram is a good way to sense check yourself, and you tend to get a feel for the problem doing it that way. When you're interpolating, you really have to look at every number and every step of the way and say, hey, does this make sense? And if you're not experienced working through some of these problems, then it's hard to know whether your answers make sense along the way. But that comes from practice. So anyway, so now we have H2 and H3. We can find out what delta H ideal for that turbine would be. It would be the difference between H2 and H3, which is 1509.2 BTU per pound mass minus 967.7 BTU per pound mass, and that equals 541.5 BTU per pound mass. And that gives us part of what we need for this equation up here. It gives us H2 minus H3, and again we have the efficiency, but we still don't have m dot. So now we have to look at the waste heat boiler. So I mentioned earlier that we were going to write this equation, Q equals MC delta T for the primary side of the heat exchanger and m dot delta H for the secondary. And I mentioned that we were going to include the efficiency as well. So now is the time we want to do that. And I'll write it this way. The efficiency is going to reduce the amount of heat that actually gets transferred. So I'm going to multiply Q dot on the primary side times that efficiency, and I'll use the subscript P for primary. And only that much heat will transfer to the secondary side, so Q dot S for the secondary. So how do we calculate Q dot on the primary side? Well, it's going to be m dot Cp delta T. And we know all those numbers, so let's plug them in. We have 9 pound mass per second, and the specific heat capacity was given to us as 0.239 BTU per pound mass degree Fahrenheit. And the temperature difference, we know both temperatures. We know it was 1040 going in, well, going into the heat exchanger, right? That's coming off of the primary turbine, but that's what's going into the heat exchanger. 1040 degrees F. And when it comes out the other side, it's 650 degrees F. And if you do all that math, you will get Q dot sub P equals, you're gonna get 838.9 BTUs per second, which we could put in BTUs per hour, but we'll leave it like that. And how much of that heat actually gets through to the secondary side, let's multiply by the efficiency. So Q dot on the secondary side equals 0.9, 90%, times that 838.9 BTU per second. So actually getting through, we have 755 BTU per second. And now if we want to write out what Q dot on the secondary side actually is, it's m dot. Now this is m dot for the steam turbine loop. So it's not this m dot, it's m dot for 1, 2, 3, 4, which we're going to write as m dot delta H. Specifically, that's the difference between the enthalpy at state 1 and state 2, which is either side of the heat exchanger, m dot H2 minus H1. And we don't know m dot, and we know H2, but we don't know H1. So that's why we have to continue around the cycle. We do know states 2 and 3, so let's talk about state 4. So we're going to make an assumption for the pump. On the output of the condenser, which is the inlet to the pump, we'll assume that all the steam condenses. So if all the steam condenses, then the quality of the input to the pump is 0, which is to say it's a liquid. And it really has to be. The reason we can make this assumption is because the pump can only pump liquid. So this is a fair assumption. I wasn't sure if I could make it because after the turbine I was kind of thinking maybe we had to use the entropy there and we had to interpolate and all that. But I think it's a pretty fair assumption for the pump. And if that's the case, then we know the quality equals 0, and we also still know that the pressure doesn't change across the condenser. The pressure is the same, which is 2 psia. So we can use the same table that we did before, which is the saturated steam table, and we really want this number, H sub F, which is 94.02 BTU per pound mass. That's going to be the enthalpy at state 4. So now we have to deal with the pump. The pump is also not 100% efficient. It's only 60% efficient. So the difference in enthalpy between state 4 and state 1 has to account for that efficiency. But we can start by asking ourselves the question, what would the enthalpy be at state 1 if the pumping process were isentropic? Well, there's a formula that we can use which tells us the work done by a pump, which is the change in enthalpy that it causes. And that's formula 27.24, which can be found on page 27-5. And that formula says that the work done by a pump, which is the same units as delta H, this is going to become our delta H, can be approximated as the volume, and that's the specific volume, of the liquid times the change in pressure, because that's really what a pump does, right? It increases the pressure, so there's some delta P across that pump. And specifically for us, this equals the specific volume times P1 minus P4. So now your question is going to be, how do we find the specific volume? Well, we did say that state 4 was fully defined on the basis that we knew the quality and the pressure. We were able to find the enthalpy. So we can go right back to the same line on the same table yet again, saturated steam table, and pick off the specific volume. So I'm looking that up, and I'll put it again here, but it's app 23b, and we're using the same two facts. P equals 2 psia and the quality equals 0. Based on all that, the specific volume is 0.01623 cubic feet per pound mass. And that's what we're going to plug in here. And then P1 and P4, we know P4 is 2 psia. We also know P1. Why do we know P1? Because we know the pressure after the heat exchanger, or the boiler, if you will. The boiler doesn't actually change the pressure. It changes the temperature. And incidentally, it changes the state. So the liquid water is changing to a vapor, but the pressure isn't actually changing. The only time the pressure changes is during the expansion process through the turbine and during the pressurization process through the pump. But states 1 and 2 have the same pressure. So we actually know P1. So we can find the work done by the pump. It's our 0.01623 cubic feet per pound mass times 900 psia minus 2 psia. And now the other thing that's going to happen here is we have pounds per square inch and cubic feet per pound mass. So if we want this to come out in BTU per pound mass, we're going to have to work on units. So let me actually just do the units out so we can deal with that. We have cubic feet per pound mass times pound force per inch squared. We want to get rid of inches squared, so we'll do 144 inches squared over 1 foot squared. And that gets rid of 2 of the feet with this, and then the inches squared. And then we really don't want pound force, we'd rather have BTUs, so we can multiply by 778 foot-pound force is 1 BTU. Now I'll get rid of pound force. So after that, we'll be left with BTU and pound mass. So we need to multiply by 144 and divide by 178. So I'm just gonna, since we did the units down below, I'm just gonna put those numbers here. And we get W for the pump equals 2.7 BTU per pound mass. So it's pretty small. The work done by the pump, the enthalpy that's added is not a ton. However, this assumes that the pumping is ideal. Remember we said this is going to assume it's isentropic. So the actual work done by the pump, and this gets a little counterintuitive as to how you deal with the efficiency. I always get tricked up by this, but remember what you want to happen. If you're in the business of operating a turbine, you want to get more work out. So the efficiency is going to be a number less than 1. It's going to multiply by the delta H and make it smaller. You're going to get less out than you want to. On the other hand, when you're operating this boiler, you want to come in at as low a temperature as possible, or as low an enthalpy as possible, I should say, so that you can do as much heating as possible to reach the hottest possible condition at state 2. So what ultimately happens is that the pump increases the enthalpy more than you would want it to, so that the boiler can't do as much heating as you would like. So the work done by the pump is actually going to be more, actually, than the ideal work done by the pump. So we have to divide this number to find the delta H. So let's write that out. This is work done by the pump ideal. Work done by the pump actual is 2.7 over 0.6 for the 60% efficiency, which is 4.5 BTU per pound mass. So H1 then would have been H4 plus the change in enthalpy because of the pump, 2.7, but now we're finding H1 prime, the actual H1 state. If it's not isentropic, it's not 100% efficient, we actually have to add the 4.5 BTU per pound. And just recall that H4 was this 94.02. So 94.02 plus 4.5, we're going to get 98.52 BTU per pound. Okay, so we're almost home. Now we can get back to when we were writing the secondary side of the Q dot formula. We said we had Q dot from the primary, including the efficiency, and then equal m dot delta H, and we didn't know m dot, and we knew H2, but we didn't know H1. Now we know H1. I could be even more specific and say H1 prime because we took into account the efficiency. So now we can find the mass flow rate. So let's solve that equation. We had Q dot equals m dot h2 minus h1 prime, we can isolate m dot equals q dot over h2 minus h1 prime, which equals 755 BTU per second, over h2, which you have to go back up if you want to see what that is, but it's 1509.2 minus 98.5. Those units are BTU per pound mass. And that gives us a mass flow rate of 0.535 pound mass per second. And that's the answer to B, so we had to find B en route to finding A. Now for A, they wanted to know the gross work output, or the work done by the turbine, and we had written the formula earlier, but let's write it one more time. W dot equals the efficiency of the turbine times the mass flow rate for the steam turbine cycle, which we now know, times delta H. What delta H? Well, again, it's the efficiency times the mass flow rate, and it's the difference between H2, the inlet to the turbine, and H3 after the turbine. So this is capturing the change in enthalpy during that expansion process. And now we know both enthalpies, mass flow rate, efficiency, it's all there. Let's plug in the numbers. 0.8 for the efficiency, it's 80%, times 0.535 pound mass per second, as we just found. H2 is 1509.2 BTUs per pound, minus 967.7 BTU per pound. And if you do all that out, you get 231.8 BTU per second. And they wanted the answer in horsepower, so we're going to have to convert. We'll have to multiply by 778 foot-pound force per BTU. That gets rid of BTUs. And we want to go to horsepower, so we'll need to do 550 foot-pound force per second. And that'll be the denominator over 1 horsepower. So the foot-pound force goes away with this. And then the seconds is in the denominator of the denominator, so that actually cancels with this. And we just end up with horsepower, which is what we want. So times 778 over 550. And we finally get W dot out 327.8 horsepower. And that is the answer to A. So that's it. I hope you enjoyed this problem. I really did. I think it's kind of neat to work your way around the steam, around the cycle, using the steam table to figure certain things out, interpolating, making assumptions, testing those assumptions. We even used Q in equals Q out. So there's a lot of good thermal concepts baked into this problem. This is a good problem for putting it all together. So I hope you got a lot out of it. If you have any questions or anything's unclear, go take some time, do some other problems, come back to it, try this one again. If you still have questions, let me know. Send me an email, leave a comment, ask a friend or study partner. Don't just leave it and not make sure you get a handle on it, because this is a really good problem for illustrating a number of those concepts. We'll see you in the next video.